Good afternoon. Good afternoon, everyone. In the previous lecture, we were discussing about the usage of a particular MCMC library called Hamiltorch. The goal remains the same. We want to be able to generate samples from some P of x, right, given the unnormalized density P tilde. Can someone tell us why do we not get samples from P of x, but why do we have access only to P tilde of x? P tilde is the normalized density. Why is that? That we have access to P tilde, but we don't have access to P of x. So generally the way we get the P tilde is we multiply the prior and the likelihood and we get the joint, but that joint is not the posterior, the joint is proportional to the posterior. The posterior has a normalization constant, which is one of the harder things about doing Bayesian inference. One of the reasons why we end up doing things like MCMC or variational inference or Laplace approximation, right? We don't have easy access to the normalization constant. So what a practical MCMC library like Hamiltorch or Blackjacks requires is to just give a log probability function. We looked at a simple log probability function where we knew the distribution, so we were cheating here. And we saw that we had to give in a certain set of hyperparameters or certain set of state and parameters. One of them was the initial state, and then we said that we'll move about in that space and try to, our goal would be to be able to get more samples where there is more probability, right? We want the number of samples in a particular region to be proportional to the density in that region. Right? That's a broad goal. And we end up giving certain hyperparameters such as the step size, how big or small should we have jumps when we are exploring the space, number of steps per sample. This we said is something specific to Hamiltonian Markov Monte Carlo like algorithms. And when we ran this, we saw that we got a trace like this. This is the parameters over time. And if we were to plot the density of the samples obtained from these trace, so it's often called a trace plot, it quite matches our distribution. Not exactly, quite matches our distribution. Then we said that let's look at a different example where we have mixture of Gaussians. So we have two separate modes, right? So perhaps if we start with -2, we'll want to look at samples in the vicinity, right? But at some point we also want to go to a unexplored island, which is the next mode. So therefore we need to have certain probability of going even in the spaces where the probability density is lower. Generally you want to sample more at the places where you have higher density, but you still want to be able to sample at places where you have lower density. So then we looked at this and we obtained the trace plot for this particular distribution, something like the following. We can very clearly see that the samples are in certain states. So at this point it's in state with mean 2, at this point it's state mean -2 and so on. Then we took the more realistic example where we have access to an unnormalized distribution, we don't have access to the normalized one. We took that one as P tilde of x, which is the normal distribution multiplied with z, where z is the normalizing constant for a univariate Gaussian, and we can clearly see that the unnormalized and normalized distribution look quite different in terms of the amplitude. That is the only difference, but we just give the access to the log prob of the unnormalized density, right? And we give it to this MCMC algorithm, and we are able to obtain samples which match the density of the normalized density. Then we took a more realistic example for coin toss where we took the prior and the likelihood, and therefore we get, so we start with log prior, we also get log likelihood, and therefore we can get log joint, which is the log prior plus log likelihood. Here we said that let's work with theta, which is the probability of getting a heads, but we encountered a particular problem. Can someone tell us? So theta should be between 0 and 1, but when we are making certain jumps, we are evaluating whether certain theta is going to be valid or not. That particular proposal does not really know, right? So the safer option is to work with the logit space, and you internally convert the logits to probits. probabilities, and therefore we were able to get quite a matching posterior using this particular form also. Then we try to solve for linear regression. So now we have two parameters, theta naught and theta 1, right? And we did exactly the same. We started off with the log prior, which is just normal distribution we assume over each of the parameter. We can also calculate the log likelihood, which figures out mu hat, assumes a certain variance, in this case 1, and therefore we can calculate log posterior. We give this log posterior to the MCMC method and it generates samples for you. And once we do this, we can obtain the posterior for the two parameters, right, or for the overall. And once we have the posterior, we can get the posterior predictive. So we did this using linear regression. We said that we can also do the same thing using a neural network, right? Now you have a prior over each of the weights in the neural network. You have an overall likelihood function. So therefore you can get a posterior, therefore you can get a log posterior. You pass this log posterior method to a sampler, and therefore you are able to generate samples corresponding to each of the individual theta i's from the posterior. Then we looked at certain other methods. We also looked at this problem for classification, where we interestingly saw that this was a predictive classification boundary, which looked fairly good. It's able to do a very good job. What we also saw was that there's a lot of uncertainty moving away from this zone, right? So therefore we're not only looking at the predictions, we're also looking at the uncertainty. Good. Any questions from this to this point? Okay, so today we'll study on what makes these algorithms run, what makes them possible. So the full form of MCMC is Markov chain Monte Carlo. The Monte Carlo part we have already seen multiple times. Today we'll be looking at the Markov chain part of this. Right. So the place where we encounter Markov chains is when we are trying to look at some sequential modeling tasks. Right. So you might not have used hidden Markov model like models, but you may have heard of things like LSTMs or RNNs. Right? That's just the way things have changed over the past few years. People are first now exposed to LSTM RNNs as opposed to they're exposed to things like HMMs. So in general, whenever we look at any time series data, for example, things like your accelerometer data, if you're walking, your acceleration data will exhibit certain patterns. You can leverage that, and then you can figure out the step count, right? Or if I'm speaking something, each of whatever I'm speaking currently has an impact on what I'm going to speak next, right? So there is a sequentiality to the data set. I cannot really ignore these things, right? Or if I'm trying to estimate the solar produce, right? So the solar produce would have been very nice till now, but just few minutes back it started raining, right? So what happened? In general, when we'll think about solar produce, we'll probably say that in the month of October there is no rains in the western part of India. We would generally have a high amount of produce. But today, if you looked at the trend, it would have been going up. The solar produce would have gone up. Then suddenly it would have dipped just because of the clouds and the rain which have occurred. So whatever I saw at 11 a.m. has an impact on what I will see at 12 noon and so on. Right? So these are all time series based problems. Similarly, stocks. Whatever price I have today will have an impact on whatever price I have tomorrow, but there are a lot of dynamic patterns, lot of other factors which also come into play. So one way to look at this is so whenever we have time series, we also have to make certain limiting assumptions, right? And one of that particular assumption is known as a Markov chain, which says that if we look at these different states, let's make a simplifying assumption that a day can only have two states. It could either be raining or it could be sunny, right? So what we're saying is that let's assume that this is a sequence of states, rain, sun, rain, sun, rain, sun, so on and so forth. A Markov chain says that given the present observation could be either sunny or rainy, the future is independent of the past. It's a very nice statement. So let's assume that x of t plus 1 is trying to encode what state you will be at time t plus 1. It could be either be sunny or it could be rainy. So what this statement is trying to say is that the probability that tomorrow will rain, given that previous t days observation, is only dependent on whether it rained today or not. Right? Let's assume that we are in this particular Markov chain. We are at day 12. The probability that day 12 would be sunny depends only on what we had at day 11, right? Or knowing day 11, you know everything about the history, right? So we are trying to compress all of that information into just one state, the previous state. There is a lot of information, but you're trying to just compress it, right? So this is known as the first order Markov chain, right? Or you could also consider this for a text based task, right? My next word is only dependent on my current word, right? Let's pick up this line. You know that it usually rains for a few days in dash. What do you think is the most probable word? You know that it usually rains for a few days in dash. Fill in the blanks. One of the answer I've given is succession. Can you think of something else? In continuity. You know that it usually rains for a few days in dash. Let's make a limiting assumption. First order Markov chain, right? The probability of the next word depends only on my current word, right? So therefore I have to make this guess. If I'm assuming that this is modeled by a first order Markov chain, my only historical information that I can have access to is in. Knowing only in, do you think it's feasible to write succession? What could we have? In India, in whatever, right? In happiness, whatever. Sorry, what do you say? In some month, right? So just given a single current word, predicting the next word is fairly hard for such a problem, right? For a text based problem, but we will make this assumption. This is the first order Markov chain. A second order Markov chain would have considered two prior historical states, right? Now some of you who have studied similar things in either language or vision or time series based models, you would also be able to relate this to the unigram, the bigram, the trigram kind of models. This is exactly the same thing. Right? But this is the most important statement here. Given the present observation, the past and the future are independent of each other. So therefore, the only thing I need to be able to estimate the future is the present, which also means that I have to have a way to encode all of that information in a particular state, or I have to make this assumption. So we typically denote a graphical model for a Markov chain, specifically in this case a first order Markov chain. First order Markov chain means that there is only first order dependencies. There is only one historical state which needs to be considered, is you go from x1 to x2 to x3, so on and so forth, right? In a second order Markov chain, what do you expect to change in this graphical model? So then x3 is not just dependent on x2, but it's also dependent on x1. Right? Let me pull up the other slides to show this. And this is how a second order Markov chain might look like. The probability of xt plus 1 given all of the history depends on xt and x of t minus 1 on the previous two observations. That's second order Markov chain. So in general, you can consider any k lag Markov chain. So therefore, so we make the simplifying assumption to make our life easier whenever we're trying to calculate the likelihood or the probability of a certain set of states, right? So the probability of observing t plus 1 observations, we could just break it down as probability of the first observations observation times the probability of second observation given the first observation, and so on and so forth. We just have pairwise relationships. Right. So now we can take a few examples to consider this. We could have considered some examples could be rain and sun. Another example could be that for some reason you choose to change between a fair and a biased coin, right? And another could be the state of an appliance. It's either on, off, right? Why do you think Markov chain makes sense for the weather example? We said that it's a limiting assumption. We only care about the previous observation. Why is it an okayish assumption for the weather example?
Because the information of weather like a few days ago is not really encoded anywhere. Like all the for weather, all the information we have is in the present.
Okay. We also generally know that at least for a lot of most of India, we see certain seasons, certain patterns, right? In the monsoon only it generally rains. In the summers it is sunny. In the winters also it's mostly sunny, it's dry, right? Whereas I've been to certain other countries where if you don't regularly see your weather app, you would be doomed. So it's very sunny in the morning, in the evening it's chilly, right? So there the weather changes very, very rapidly. In India more or less it's stable, like that's what at least we have seen till now. So the first order Markov chain is a reasonable assumption. What about the state of an appliance like an AC? If the compressor is on, it will remain on for a long time till the temperature has been attained, and then the compressor will turn off. Then it will remain off for a long time till the temperature has become warm again. So the compressor again needs to kick in. Right? So again, these are relatively valid assumptions that we've taken. How do we characterize a Markov chain? What do you think? Whenever we are talking about characterizing anything, we are talking about the parameters of that. What do we need to characterize any Markov chain that we've seen thus far? We need to know the states. Let's make a simplifying assumption that we have a discrete state Markov chain, right? Our states are discrete in the sense that they're rainy, sunny, fair, biased, or on and off. Okay, so we need to know the states. What else do we need to know? The hint is in this equation, right? So we need to know probability of x1. We need to know that at time t equal to 0 or t equal to 1, is my state rainy more likely or is my state sunny more likely, right? It has to be a probability distribution, assuming that there are these two only states. Okay, so this is known as the prior probability. Don't get confused with the prior over there. In this case also it's a prior, but it's a categorical distribution that we use. Okay, what other term do we need? Someone already said that. Okay, Arun, you said that. Can you repeat? Transition probability. So what is the probability of going from fair to biased, biased to biased, fair to fair, and biased to fair? We need all these transition probabilities, right, in order to characterize this. So what we say is that let's look at this particular example. So what we're saying is that starting has, if you start from time t equal to 0, there's a 60% chance the first day it will be rainy and a 40% chance that the first day would be sunny, right? Now when it is rainy, there is a 70% chance that tomorrow will also be raining or the next observation will also be rainy, and there's a 30% chance that the next observation would be sunny. Whereas if we are at sunny state presently, there is a 60% chance that the next observation will be sunny and a 40% chance that the next observation would be rainy. So this is known as a finite state machine way of looking at the probability distribution or the parameters of the Markov chain. Right? Importantly, you will see that from a given state rainy, the outgoing edges must sum to 1, right? Because it has to go somewhere. And what about incoming? Should that also sum to 1? Should the incoming edges also sum to 1? No. Okay. So this is one particular method of describing a Markov chain, one particular notation of describing a Markov chain. We can also use a couple of others. So we can also create a tabular notation for representing a Markov chain. Right? This is telling that I am going from state at t minus 1 I am at a particular state, and at t I am at some other state. So I can correspondingly have this probability of going from xt to xt minus 1 via aij kind of a notation. Right? How many entries will we have in this table? How many rows do we have in this table? Each, let's assume that there are k states. Previous example we had 2 states, right? Rain, sun. How many entries will we have in the transition table? K square. Rain to rain, rain to sun to rain, sun to sun. Right? There will be k square such combinations. We also saw the same using the finite state machine. Right? Rain to rain 1, rain to sun 2, sun to rain 3, sun to sun 4. The same thing we could have written in a tabular form. So we have seen 2 different ways. One is the finite state machine diagram, the other is this particular tabular form. Is there any other data structure we could have used, which you typically use? What kind of a matrix? Okay. What is that called? State transition, or something else which you study in your DSLI courses? Adjacency matrix. Right? This is the finite state machine form, and this is the adjacency matrix form. Right? So I will typically be using the adjacency matrix or the finite state machine wherever they make more sense. So let's first, before understanding how to get samples from Markov chain, let's try and take a look at what would happen. So at this point, my prior probability is telling the probability of the first state. It's 0.5, 0.5. Let's take it all the way down. Right? Now you see that the graphical model has also changed. The finite state machine model has also changed. From start, I have to go to sunny. I will not be able to go from start to rainy. Right? If I am to generate, there is some particular transition matrix also. It's in a k by k matrix form. Let's just generate some samples. Importantly, the first sample has to be sunny. Then from sunny, there is a 50% probability of going to rainy, and then there is another 50% chance of going to rainy. Right? But the important thing we've noticed here is that the first state always has to be sunny. Let me reset, draw again sunny, restart, again sunny, because the probability is 1. But if I had made it 0.7, right, enough to simulate, again sunny, let me redo, rainy, right. There was a 30% chance that the first state could have been rainy. First day, the first observation could have been rainy. So therefore, the prior probability is trying to encode the first observation, and the transition matrix is then trying to incorporate how the state jumps happen. Right? So let us now make it little extreme, and through these sliders you can see that they are summing up to 1. These things are summing up to 1, because that is the outgoing probability from currently being in a sunny state. It has to go to either sunny or rainy. If I make it 0.9, and for rainy also I make it somewhat symmetrical. Now very likely whatever state I start within, I will end up at the same state for a few observations. I start with rainy, I remain in rainy. I start with sunny, I remain in sunny. Start with rainy, there is a 10% chance of going from rainy to sunny, and which is happening over in this. Right? What if I took it to the extreme? Once I'm in sunny state, I will remain in sunny state. You can see the corresponding change in the finite state machine also. There is no outgoing edge from sunny to rainy. if we simulate this, once we are in a sunny state, we will remain in sunny state, right? So while these may seem like very trivial examples, we will be making use of some of the things which we have seen currently, right? One of the things we have seen is that all of these states are not possible. You'll not be able to visit all of these states in certain Markov chains. That is an important property which will come, right? So now, how do you think we can write some code to generate a Markov chain like this? You already have all the basics for doing this now. What do we need to do? Given a prior probability, which is a categorical distribution, and a transition matrix, which is a k cross k matrix, how would you be able to generate such a sequence? Okay. Okay. Okay, excellent. You have said 90% correct. The first, you've not told about the first state, first observation. Okay. Yes. So if we look at the code for this, I have set my prior distribution to be 0.5, 0.5, and I've created my transition matrix to be 0.9, 0.1, 0.2, 0.8, and my states are 0 is sunny, 1 is rainy, right? So this is the probability of going from sunny to sunny. 0.1 is going from sunny to rainy, 0.2 is from rainy to sunny, and 0.8 is from rainy to rainy. And initially both of these states are equally likely. So if I look at my method, my first observation or the 0th observation is taken from a categorical distribution, which is the P distribution, right? So because it's 0.5, 0.5, each of the outcome is equally likely here, but in general it's a categorical distribution and I can sample from it. Once I have data for a 0th iteration, I can get data for the ith observation. So it will be either be sunny or rainy, right? So now if it is sunny, I will then look at the transition probability going the row corresponding to sunny, right? And this is the row corresponding to rainy, right? So I will then look at if it's sunny, then it means that my data of 1 is also going to be sunny with 90% probability and it will be rainy with 10% probability. So I need some way to encode this, which is looking up into that table. So data of I is a categorical distribution with A of data of I minus 1. Right? A of data of I minus 1 is just giving you a lookup into this transition matrix, adjacency matrix, and then it's again a categorical distribution. I can draw from it, and then I'm just writing a mapping between the states. So you can see that for one particular random seed, I get rainy, sunny, 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 so on and so forth. For some other seed, I get something different. For yet another different random seed, I see rainy to sunny to rainy, right? So that's the algorithm which we have looked into. So we'll be now looking into certain specific properties of Markov chains which make them amenable for MCMC. Wait. So the important thing that we have thus far looked is, let me actually go there. Right, so we look back at the slide many times. We said that we wanted to compute the posterior predictive. We would typically use Monte Carlo for this, which means that we are trying to solve integrals of the form I equal to integral of fx px dx. Generally, we don't have px, we have p tilde of x. And we can approximate this by 1 over n summation fx of I. Importantly, where xi is drawn from px iid. Right? Today's topic is Markov chains. Markov chains do not give you IID samples. Right? They'll give you dependent samples. And typically we end up using anomalies density. We have also looked at, so we are now trying to understand why are we going into MCMC methods. The previous methods like transformation based methods or the rejection importance sampling, they are very inefficient. They have a very low acceptance ratio. So therefore, we end up picking something which is the Markov chain Monte Carlo algorithms. We have looked at this kind of a Markov chain earlier. This is the exact same Markov chain which we have been drawing. I have drawn the start, sunny and rainy. This is a finite state machine view of this. And I am again drawing the prior probability and the transition matrix. Right. So now I will want all of you to work out certain things in your notebooks. This one is not very difficult. You don't need a notebook for this. What is the probability of the first day being sunny or day 0 being sunny? 0.5. That is coming from the prior probability table. Okay, next question. What is the probability of it being sunny on day 1? Sunny / rainy on day 1. You need to do some calculations for this. $0.55 and 0.45. Is that what everyone gets? Okay, Kush, do you want to tell how you got this number?
First day would be, if the first day is sunny, then probability of the next day to be sunny is 0.5 into 0.9.
Okay.
And if the first day is raining, then probability of the second day being sunny is 0.5 into 0.2. And as we add both of them, we get 0.55.
Okay, good. So we have two cases. If x0 equal to sunny, then probability of x1 being sunny is 0.9. For that, we have to look at the transition matrix. If x of 0 is sunny, then x of 1 being sunny is 0.9. If x of 0 is rainy, then x of t plus 1 being rainy is 0.2. We know these things. But probability of x0 being sunny is 0.5 and probability of x0 being rainy is 0.5. So therefore, the overall probability of day 1 being sun is 0.5, which is the probability of x0 being sunny, multiplied by the transition from sunny to sunny, plus day 0 being rainy and the transition from rainy to sunny. It comes out to be 0.55, and similarly for p of x1 equal to rainy, you could either calculate this or just subtract 1 from it, because these are the only two states you have. Okay, day 2. Can someone tell me the numbers for day 2? So this is where again the beauty of Markov chains come in. And again, for those of you preparing for placements, etc., you should try to look at the relationship between what we're writing and dynamic programming. Okay, does anyone have an answer? Sorry? 0.58 and 0.42, okay. So once you have figured out this answer, can you tell me the answer for a tth day? Okay, let's look at the answer for the day 2. Probability of x2 being sunny. Now, importantly, now you are considering the beauty of the Markov chain or the assumption that you have taken. You only need to now consider whether the previous day was sunny or rainy, and that probability we already know. Probability of x1 being sunny was 0.55. So we just plug that in, times remaining from sunny to sunny, plus the probability of rain was 0.45 previous day, and going from rain to sun is 0.2. If we do the calculations, we will get 0.585 and 0.415. Right. Now for day t. Can someone tell an answer? You could write a for loop, right? That's one way to do. Can you do without a for loop? A into xt minus 1, but xt of minus 1 also I want. So you have given me the recurrence relation. I want the full answer. Again, this problem might not seem very different from the Fibonacci sequence. We also get in terms of certain matrix powers, right? So that's the hint. Raise something to some power and you'll get a good answer. You'll get the correct answer. You only have two matrices here, pi and a. A? Okay. So first let me give you the solution and then we'll work through the code to understand why this is the case. So I'm saying the distribution of x of t is given by pi equal to pi into power of a comma t. So it is raising the matrix A to the power t. At t equal to 99 and t equal to 100, if I do this, I get pi equal to 0.67 and 0.33. So sorry, we should just have considered this one to be p, the prior probability, instead of pi, the right one. This one, let's assume that this was p and not pi. We get the distribution as 0.67 and 0.33. Right? Importantly, this is at both t equal to 99 and t equal to 100. What do you understand from this?
As time increases, the probability of sunny increases as compared to probability of rain.
As time increases, the probability of sunny increases with respect to probability of rain. Okay. But my question is simpler. At t equal to 99, you get the probability of sunny being 0.67. At t equal to 100, the probability of sunny is exactly the same, 0.67. What do you understand by that? Okay. A to the power 99 is the same as a to the power 100. What implication does it have here? Yes, go. The probability of sunny and probability of rainy has converged, right? Or this particular Markov chain has converged to some distribution, right? This was some Markov chain. After certain number of steps, the probability of sunny and probability of rainy does not change, right? It means it has converged to this particular distribution. In this case, the particular distribution is a categorical distribution with 0.67 and 0.33 as the probability, right? Does it mean that I will not see variation in terms of the states I am drawing? Yes, no? We can still see the variation, but the distribution is 0.67 and 0.33. From 0.67 and 0.33, you can draw various random vectors, right? So we call such a Markov chain to be converged, or this particular distribution is known as the stationary distribution for this Markov chain, right? Let's look at some code now. So I'm trying to now generate the distribution or the probability vector corresponding to sunny and rainy at any given point, at any given time t. As I mentioned earlier, we could simply write a recurrence relation or a forward pass, right, or a for loop, right. So the probability of being sunny at time t0 is just p0, and the probability of rainy at time t0 is just p1, p of 1, right, where p was the prior probability, right. Now the probability of the probability of Sunny at time t is given as the probability of Sunny at time t minus 1 times the transition corresponding to from Sunny to Sunny plus the probability of it being rainy at t minus 1 multiplied by the transition probability going from rainy to sunny. Okay, does everyone follow this? Probability of it being sunny today is the probability of being sunny yesterday times the transition from sunny to sunny plus probability of it being rainy yesterday and a transition from rainy to sunny. Similarly, probability of being rainy today is sunny yesterday and the transition from sunny to rainy plus rainy yesterday and a transition from rainy to rainy. So, this is just encoding the 4 different elements of the transition matrix, and this is where the hint to the matrix power also comes in, right. So, we have multiplied PS into A00, PR into A10, PS into A01 and PR into A11. This should give us a hint of how the matrix power was coming in. For 20 different iterations, I just append this, call this function, and if I look at this PS and PR and I plot these, right. So, can we see that though they both started at the probability 0.5, 0.5, after a certain number of iterations, they seem to have converged to 0.67 and 0.33, right. So, now let us look at what is happening. We should first look at what matrix power operation is. So, it is the same as A multiplied by matrix A, or we can verify that both of these matrices are the same. So, now we can try and attempt to write a vectorized version of getting the convergent distribution, right. So, what we are saying is that probability of sunny at time t equal to 1 is P0 into A00 plus P1 into A10, we have already seen this. Similarly, rainy at time t equal to 1 is P0 into A01 plus P1 into A11, or the distribution at state t equal to 1 is P into A. If we look at this, these are exactly the same, right. P into A gives us 0.55, 0.45, and similarly P sunny at t equal to 1 and P rainy at t equal to 1 is the same. We just need to stack them up, right. So, you just need to consider the way these operations are done and break down the matrix product into this way. And because of the way the Markov chain is constructed and we depend only on the previous probability, we can directly just do for time t equal to 2, we can do P into A or P into torch dot matrix power A comma 2 gives us the probability at time t equal to 2. This is the exact same number that we computed, 0.585 and 0.415. Now, at any time t, we can calculate this matrix product power, and we can verify that this is the convergence question which I asked you. At 99 and 100, I get the exact same numbers of it being in sunny and rainy, 0.666 and 0.333, right, which means that the convergence has already happened. Okay. So, here we started with the first state to be 0.5, 0.5, right. What if I started with a different prior probability? Let us say the probability of starting in rainy is 99% and sunny is 1%. Can someone tell me the stationary distribution for this configuration? Let me repeat the question. So, here we started with probability of sunny being 0.5 initially at time t equal to 0. You should work it out in your notebooks if you want. Now, I am saying that there is a different prior distribution that we could have given. Probability of sun equal to 0.01 at time t equal to 0 and rain is 0.99. Can you tell me the stationary distribution for this? So, the hint is whenever I am asking you questions which are very hard to compute on pen and paper, they do not require computation. Sunny 0, rain 1? No. Yes. Same as this one. Suraj says it is the same as the current one. Can you tell why? So, one, the answer is because I gave you that hint. You don't have to do any computation. Let's look at this. You can start with 0.9 rain, 0.1 sun, or 0.9 sun and 0.1 rain, or 0.9999 sun and 0.001 rain. But if you do the torch.matrix power of A, the important thing is that it's the A to the power something which is giving you the convergence. Right? And you still have each of the state is visible, is reachable from the other state. Right? You start with rainy, you will have some non-negative probability of reaching sunny and vice versa. So if you run this, irrespective of what prior probabilities you choose, the distribution will be stationary with, you will have the same stationary distribution after some number of iterations. Now, what could be a way to check for stationarity? I gave you an example that the 99th and the 100th distribution were exactly the same. So we could just say that so we obtained the PS new as PS into A, and in an iterative way, if you don't see any change or the change is below a certain epsilon threshold, then we can say that it's converged. This is an iterative way to do this. We could also do it in a more linear zebra way, where I can tell you I can figure out the distribution exactly. Right? Let me show you a worked out example for this, or why don't you work it out yourself? Right? So what we're saying is that right. So distribution pi is said to be stationary for a Markov chain with a transition matrix A if pi equal to pi into A. Right? So if you have a certain probability of being in a particular state, you multiply that with the matrix A, post multiply, you end up with the same probability distribution. Right? So how would you solve this? You could go the linear zebra route, or you could say that pi is the left eigenvector of A, etc. Right? Or if you're like me and you didn't understand that statement fully, you should then take out a simpler worked out example. Right? So let's say that pi equal to pi 1 comma pi 2. What we can say is that pi 1 equal to 0.9 pi 1 plus 0.2 pi 2, and similarly pi 2 equal to 0.1 pi 1 plus 0.8 pi 2, pi 1 plus pi 2 equal to 2, we know that. If you combine all of these equations and you solve, you will get pi equal to 2 over 3 and 1 over 3. You didn't have to actually go through anything, like you didn't have to follow an iterative procedure. And from here, can you also see that the stationary distribution is independent of the prior distribution that you have chosen, right? What you're saying is that at particular state, if I take care of all the transitions, I will remain in the same stationary distribution, same distribution. So that is the definition of stationarity. Right? You could solve it using various tricks also, QR decomposition or some other methods. Questions? Okay, I have one question for you if you don't have one for me. Can a Markov chain have multiple stationary distributions? The easiest way to think of such questions is to draw some finite state diagrams. So let me give you a hint. Draw a finite state machine with 4 states. And the next hint is, the answer is yes, you can have multiple stationary distribution for a Markov chain. And the hint I'm telling you is that you will end up in 2 possible stationary distributions. If you start with some part of the Markov chain, you will end up being in that part of the Markov chain, or if you start with the other part of the Markov chain, you will stay in that part of the Markov chain. You will never cross the 2 parts of the Markov chains, which from a graph theory perspective, you might have already thought there's a disconnected component. Okay. Can you draw some finite state machine for this? Okay, another hint. Let's draw the 4 states as A, B, C, D. If you start at either A or B, you'll circle between A and B, and that is what will define a stationary distribution. Or if you start at either C or D, you'll circle between C and D, and that will give you a stationary distribution. Now try and give some numbers. Okay. There could be various things, but essentially you will have something like this, which will have a disconnected component. We have 4 states A, B, C, D. From A you can reach to B, and from B you can go to A, but B and the other part, the other Markov chain are disconnected. From either A and B you can't go to C and D, and similarly from C and D you can't go to A and B. Right. Can now someone explain why this Markov chain will have 2 stationary distributions? Anyone? Someone else? It's not yet answered. So, can you now explain what are the 2 stationary distributions that this Markov chain will have? It's highly symmetric. Okay. 0.5, okay. Yeah. If you start with A or if you start with B, the stationary distribution is 0.5, 0.5, 0, 0. If you start with C or D, the stationary distribution is 0, 0, 0.5, 0.5. Right? You will be stuck at either of the 2 islands. You will not be able to escape those islands. Good questions on this? You can also okay, so perhaps what Suraj is saying is the interrelationship between graph theory and finite state machines and some linear algebra and various things. Perhaps there are various such things. You could perhaps count some linearly independent or dependent or some things like that, and you will be able to come to such similar numbers. Okay, there is another important property called time homogeneity, which is almost always assumed when we are talking about Markov chains, simple Markov chains. So we say that the transition probabilities are independent of time t. That is it. So it's the transition matrix that you create is independent of time t. So we have the same transition matrix A for all time t. That is it. The next property is called irreducibility, which means that each state is accessible from each other state. We have already looked at examples of some irreducible Markov chains and some irreducible and some non-irreducible. I don't know whether it should be called reducible or non-irreducible chain, but I generally prefer to call it reachable or non-reachable. Are there some states which are non-reachable? Are there states which are all states which are reachable? So for irreducibility, let's look at this diagram. Is this, can you reach each state from each other state? Yes. So this is an irreducible Markov chain. Can you reach each state from each other state? No. So this is not an irreducible Markov chain. The last property is called aperiodicity, and the definition is hard. If you just stare at the definition, the greatest common divisor of the set of all possible times between return to a state is 1. Right? So you start from some particular state, you reach back to another state. You can reach back in, let's say, time t equal to 1, like in the next step, or you could reach back in next timestamp, 2 timestamps. or 3 timestamps or 4 timestamps, 5 timestamps, so on and so forth. If the GCD of all of these numbers where you can reach back to your state as 1, then your Markov chain is said to be aperiodic. Right? We could look at all of that definition, or we can look at it the other simpler one. The chain does not return in a very to a particular state in a periodic fashion. Right? This is slightly simpler, but I think if we just take an example, it becomes much simpler. So the third definition is the one which I want you to concentrate on. Can every state be reached in 2 consecutive timestamps? Right? So in order to understand this, let's go back to the simpler example. Can you reach Sunny at time t equal to 0? At time t equal to 1, 2, 3, 4, 5, 6, so on and so forth. Right? Now you look at all these numbers 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. The GCD of them is 1. That is the as per the definition. But you can reach the same state at 2 consecutive time periods, which means it's aperiodic. There is no periodicity pattern to it. Whereas if we look at this Markov chain, right? So this will require a bit of work. Why don't you create these 4 states, this finite state machine diagram in your notebook, and tell me whether this is aperiodic or not. Start with state 1 and tell me how often can you reach state 1, state 2, state 3, state 4. Is there any periodicity to those or not? You'll have to, it will be good if you can just draw this in your notebook and tell me at time t equal to 1, if at time t0 if you are in state 1, at time t1 what all states are possible, at time t2 what states are possible, time t3 what states are possible, and so on. If you write that, you will understand aperiodicity. Let's assume that you start with state 1. You don't bother about the prior distribution, because this is enough to just contradict the fact that, so just show the fact that this is not an aperiodic. That is all. You just need to have one example and show. Okay, those who have solved, can anyone come on the board and show? The marker should be there, I think.
First state is S1. From there we can only go to S2 at t equal to 1, t equal to 0. S2, from S2 we can go to S1 or S3. From S1 again we can go to S2. From S3 we can go to S2 or S4.
Okay, this should be enough. So can you note that at odd timestamps, what all states are you in? At t equal to 0, you can be at S1. At t equal to 1, you can be at S2. At t equal to 2, you can be in S1 or S3. So at odd timestamps, you can be in even states, and at even timestamps, you can be in odd states, which means that there is a periodic nature to what we have. Right? So therefore, this is not an aperiodic Markov chain. Questions on this? Oh, I had this. At t equal to 1, we can be in state 2, but not at state 1, and that also, so with this definition also we could just end it. At t equal to 1, we cannot be in state 1. So it means that we'll have to be in state 1 in a pattern which is not at, you're not at 2 consecutive timestamps, or the way the Harry just showed. Which brings us back to why we are studying all these properties. Right? So we said that we want xi to be sampled from px IID, that is for Monte Carlo sampling. But if we use a Markov chain, then the samples are not IID, they are clearly dependent on each other. But we can still use these samples to estimate the integral I if using the theorem known as ergodic theorem, which states that if you have a Markov chain which is irreducible, aperiodic and stationary Markov chain, whose unique stationary distribution is pi, then we can use the pi sample from pi and use that to compute I. So all of that maths, all of those properties, we said we looked at only to be able to say that we can use samples from a Markov chain to solve Monte Carlo problems. Right? But those Markov chains have to have these properties: irreducible, aperiodic, stationary, and that stationary distribution itself is pi. Right? So these things will make more sense when I help with the video. I show some particular video. Let me just stop the recording.